Hi and welcome. The presentation today is about alkali aggregate reactions AAR, and at the end a little bit about oxidation of pyrrhotite. My name is Børge Johannes Vigum. I'm an adjunct professor at the Department of Geoscience and Petroleum at the Norwegian University of Science and Technology in Trondheim, Norway. I also have a position at Heidelberg Cement, Northern Europe, where I am a senior project manager. Alkali aggregate reactions. This is a reaction where alkalis producing a silica gel by dissolving soluble SiO2, for instance quartz minerals, in the aggregates used in concrete. And this gel, which is produced, has hygroscopic properties, leading to expansion under moist conditions. In real concrete, these mechanisms or reaction takes place after 5 to 50 years, depending on the type of aggregates and environmental conditions. The consequences of this reaction is that you get some expansion and map cracking in the concrete. You get some constraining forces which could reduce the capacity of your concrete structure. And it will influence the material properties of the concrete itself and reducing the capacity. But also what is important that these mechanisms could initially initiate some other deleterious mechanisms like frost damage if water is coming into the cracks and so on. And also when water or chlorides coming through the cracks into the rebar, you could get some rebar corrosion. So the AAR mechanisms could also lead to some other deleterious mechanisms. If we try to go through the reaction briefly, we're starting with a SiO2 crystal, which is in an aggregate, which is within the concrete or in the cement paste. And the SiO2 crystal is on the surface balanced with the H- ion. That's the starting point. So that's the original situation. But as this crystal in the aggregate is in the cement paste in the concrete, and in the concrete in the cement paste you have a high pH, so you have a high concentration of OH- ions. So in the next step you have this OH effect. So due to the high pH or the high content of OH- ions in the cement paste, you get a reaction where OH is binding with the H ions and you are releasing H2O or water. And then the situation of the crystal surface is that the O- is balanced with the sodium ions. And then you have this situation that this reaction is happening. So you are producing this sodium or potassium silica gel plus hydrogen. And you are in a way starting to disintegrate the total or original SiO2 structure. So the crystal structure, if it is a well crystalline silica structure, as you can see on top here, then it's more difficult for the alkalis to attack the crystal lattice. However, if you have a more polycrystalline or hydrous silica in red up here, you can see that it's more easy to attack the crystal. So that will be a SiO2 crystal which is more reactive compared to the well crystallized silica. In a way, in an easy way, you could compare this. What do you think will dissolve faster in your coffee if you use this brown sugar or this white sugar? The brown sugar is more coarse crystal, the white sugar is finer, and of course the white sugar would dissolve faster in your coffee, even though the chemical composition is the same. So in a way this is similar for reactivity of minerals, SiO2 minerals in your aggregate. If it's coarse crystalline, well crystalline, it will dissolve much slower compared to fine-grained crystals. So in practice, how will this looks like? You can see to the upper left some alkali silica gel like worms coming out of the concrete, and to the right it's dried, and then the water is gone out of this gel. But this is how the gel looks in the concrete. To the picture at the bottom, you see a porous aggregate, and you see the gel is formed like droplets coming out of the aggregate. So this gel is the product of the AAR reaction. And this, you know, probably when you are buying your pair of shoes or a camera or whatever, you should not eat it, it says. So, but it's following when you're buying your products, and it is in that box when you're buying a camera or whatever, to keep the moisture down, because this silica gel have this property that it's able to keep or to drink water. So that's the properties of that gel. Also why it is expanding. When it's sucking water and it's expanding. So how could we look at this gel in the microscope? Well, we are taking concrete samples and we are making thin sections. A thin section is that you are taking the concrete and you are grinding it very fine down to approximately 30 micron thickness. And you are putting epoxy and glasses on both sides of that very thin slide of concrete or rock, but in this case the concrete. And then you have a thin section, and then you are able to see through the rock, through the concrete, when you're putting it into a microscope. So putting it into a microscope, you're able to see through your aggregates, through your concrete paste. And then you could see how the gel formation looks like. And typical reactive materials, as I have said, will be aggregates containing SiO2 minerals. So it could be a siltstone, it could where you have very fine grained quartz minerals, SiO2 minerals. Or it could be, for instance, a deformed melanite. In this, the melanite picture, the original quartz minerals, they are very squeezed, and in the way they are squeezed, ductile squeezed, the crystal lattice is destroyed in a way, so that makes it more reactive. So the reactivity could both be due to the crystal size of the SiO2 or the quartz minerals, but also the stage of the crystallinity of the materials. So looking into a thin section of an aggregate particle, as you can see down to the right, this is only 0.2 millimeters. So we have a very high magnitude. But as you can see here in these reactive particles, there will be some cracks starting to open up. And as you can see in the section to the left between the particle and the cement paste, the gel is filling out some cracks in the cement paste. You could also see to the left one air void in the concrete that is partly filled with silica gel. This is how it looks like in a microscope. This is in plain polarized light. If you are changing your filter in your microscope, here you have the crossed polarized light. There you can see that your aggregate particle in this case contains some very fine grained quartz minerals. This is a rhyolite. It's a reactive rock type, and its reactivity is due to that it is very fine grained quartz minerals. We could also put another filter into the microscope. Here you have it in the fluorescence light. We have, because the epoxy we used when we made this thin section was a fluorescence dye. So when we're putting on the fluorescence light, we could see even more in detail the main cracks, but also some minor cracks that have been developed into these aggregate particles. And those very, very tiny cracks in reactive particles, they are of course very, very tiny, but they are partly filled with gel. And when this gel starting to absorb moisture, it's starting to swell. And it's that swelling mechanisms that making the expansion. On a little bit bigger scale, this is a plan section. It's not a thin section, but it's a plan section. So we have been polishing the concrete. You can see the diameter of the aggregate to the left is 10 millimeters. So, and we are also here impregnated with fluorescence dye. And then we can see that the cracks, they're going through different reactive particles, but they're also going into the cement paste and so on. And then when you're accumulating all those very, very tiny, small cracks filled with gel, and the gel started to expand, some expansion. And that expansion could be quite severe. Here you see an example from Norway. In the middle, it was originally an expansion joint to allow the concrete to expand due to thermal expansion and so on. But as you can see in this case, the joint has been completely filled and there's no space anymore, and that is due to the expansion of the concrete. And what we also very typical see is that when the concrete starts to crack, it will develop this kind of map cracking. This is a very typical thing to see when you have some deleterious alkali aggregate reactions. You could see some similar cracks also when you have some shrinkage in concrete, in some young concrete. You could see this map cracking. But if you have some older concrete and you see this typical map cracking, it could be reason to believe that it is due to alkali aggregate reactions. In order for AAR or alkali aggregate reactions to happen, you need to have three different options to happen. First, you need to have a reactive aggregate. Second, you need to have alkalis in the system. The alkalis in concrete will mainly come from alkalis in the cement, but it could also come from alkalis externally, from freeze-thaw salts, etc., and so on. And also recent we have realized that the aggregates itself are releasing alkalis that could contribute to the reaction. But in addition to those two, we need also to have the third component, which is moisture or water. And all of this will be accelerated by the temperature. So in a case of a concrete where you have a reactive aggregate, you have sufficient amount of alkalis, and you have water, which you in most outdoor conditions will have, then you have the possibility for alkali aggregate reactions to occur. And it will happen faster if the temperature is higher. So this is the situation. So how should we then mitigate AAR? Well, we could mitigate it by using a non-reactive aggregate and cutting that top corner out of this. But in many places it is very difficult locally to find a non-reactive aggregate, and you are depending to use local aggregates, and then the aggregate will be reactive. You could also try to limit the access to water, and for most indoor constructions and so on, the moisture level of the concrete will be that low that alkali aggregate reactions will not happen. But if you are not able to do anything about the aggregate, and you are not able to limit the access to water, you only have this corner left. You need to try to limit the total alkali content of your concrete. that means you are reducing the pH. So how should you do that? Well, there are various approaches to reduce the alkali level or to reduce the pH. You could, of course, use a low alkali cement. But then you still have the problem that you could have some external alkalis from other sources. What is becoming a very common mitigating measure is to use fly ash. Fly ash you got from when they are burning coal in power plants. You get this fly ash as the product, and you can replace up to 30% of the Portland cement by mass with fly ash. And the fly ash acting in a way, it has a pozzolanic reactivity, so it's consuming alkalis. So when you are using a fly ash cement, it will consume alkalis and keep it below the level that the AAR will occur. You could also use some granulated blasted furnace slags, which could be replaced then up to half of the cement, and it also have the same effect as the fly ash by consuming the alkalis. Silica fume is a very efficient pozzolan, and that in a relatively small amount, up to 10%, will work in the same way by consuming the alkalis. But we are running out of many of these materials. Now we are also looking into new materials that could be used as pozzolanic materials, adding into the cement to consume the alkalis. One very promising option is to use calcinated clay. So you are taking natural clay, you are calcinated, burning it, you are milling it down very fine and adding it to cement. And it will work in the same way as for instance, fly ash. And you also have some natural pozzolanic materials like volcanic materials that in the same way act as fly ash and other and consuming the alkalis. If you want to read more about this in different cases around the world, I will definitely recommend this book, which recently has been published, about the alkali aggregate reactions in concrete, a world review edited by Ian Sims and Alan Poole. This book is very good and gives a lot of cases around the world and how they have been mitigating AAR and so on. But let's look at some cases. Here we have a wall in Oslo, and I took this picture back in the year 2000. It is my colleague Jan Lindgaard, Dr. Jan Lindgaard, that is sitting there measuring the width of the cracks. We went back there some 16 years later, and as you can see, Jan Lindgaard is still there, and well, the cracks, they are still there and they haven't developed that much. You have some scaling in the middle, probably due to some frost thaw issues, but you see that the cracks are there and they are developing, but it takes a lot of time. This is 16 years of development. This wall in Oslo back in 2000 again. My colleague Dr. Lindgaard is sitting there and measuring the cracks. You see the horizontal cracks there at the bottom, but 16 years later you can see that the wall is completely collapsed. So here we have some deleterious effects of the AAR reaction. In the same way, we have a very good example at the Aggregate Bridge in Trondheim, in Norway. This bridge was built in the years 1949 to 51 and has a length of 220 meters. So the concrete slab on the top is a continuous slab with a length of 220 meters. To the left, the bridge is fixed. But to the right, which is into the city centers of Trondheim, the bridge is able to expand. So at the right side of the bridge, they had at the end an expansion joint originally. This is same bridge from the other side. So to the left you have the side where it is to the city center, where it's able to expand, and to the right it was fixed. So what happened to the top deck of that bridge is that it started to expand, and after 50 years or so you could see that it has been expanded up to 200 millimeters. That means that it's fixed on the right side, but it's expanded to the left side. So the columns on the left side were kind of bended like bananas, and the columns themselves were also cracked due to AAR. So you could see the columns, they are cracked, and they were most cracked on the west side. And that was due to that the most rain are coming from the west into the columns. So there will be most wet on the west side. And there have been some crack development and measurement of the crack development and the relative humidity of these columns. So the way to repair this, because the expansion joint that originally was 20 centimeters was completely closed, so they needed to reopen that one, and they also needed to take the columns up to the right position again. So what they did, you could see the picture up to the left, they blasted away by explosives the upper 1 meter of the column, and they straightened the column up again and fixed it with new concrete. So if you are walking under the bridge today, you can see the original place of the columns, and that they have been moved and refixed again 200 millimeters or 20 centimeters from the original position. So this is, but of course during the next 50 years or so, the bridge will still continue to expand, and then maybe after some decades they need to redo this rehabilitation and repair again. We have also done some trial repairs on the columns of this bridge, where we wrapped some carbon fiber around the columns. And the carbon fiber is working as a confinement, keeping the cracking and the expansion. And we have been having some end studs and measuring the expansion, and we see that the carbon fiber actually is able to keep the expansion when you are wrapping carbon fiber around the columns on this bridge. Here is another example from Norway. You can see this typical map cracking on the concrete on the top of this bridge. But in this case, the main forces have been concentrated in one point, and as you can see in this part of the bridge, you have one major crack. So this is just showing the forces of the expansion of AAR when it's happened in concrete over time. Another bridge in Norway, to the right, you could see that you have some cracking with the blue arrow is pointing. There's where the water is drainage from the water deck on top. So to the left on that picture, you can see there is no cracking, but where the water is drainage from the road, you could see some cracking. And there is showing that if they were able to bring the water away from that part of the concrete, you could stop further expansion. But what they did here, to the picture to the left, they did some repair, but they did not do anything with the water coming from the top. So after a few years after the repair, you still see that the cracking at the picture to the left is starting to occur in the same region again. Here we have a bridge in northern Norway, as you can see, close to sea, so there will be some sea water spraying over that concrete. And when you are starting to get some open cracks in map cracking in very vital concrete element like this, you have a big problem. So it's a question because you have this map cracking opening and chlorides from the sea water is coming in and so on, and that makes quite a big challenge. Another picture here also showing that when we have a bridge with some columns, the part of the columns which is sheltered from rain, nothing happened, but in the part where it's not sheltered, you see that you're starting to get some map cracking. So it's very important to realize the difference. If you have dry conditions, then it will not happen, but if you have some rain, enough humid conditions, then map cracking can start to occur. Here is a Norwegian dam called Hundefossen. They realized in that dam that they started to get some problems of opening and closing the gates. As you can see to the right in the picture, there's some gates where you're opening and closing for the water to go through there. But they had some problems of opening and closing the gates, so it was obviously that the whole structure was deforming and expanding. They realized that the problem in this structure was due to AAR, and you could see some of the movements here. What is interesting to see the shadows of the railing, because the shadows showing that there's been some quite big movement in this structure. Also, if you go inside, this is inside the dam, you can see some major cracks at the end of that wall, but you can also see the rail, how deformed they are due to the heavy deformation, due to expansion by alkali aggregate reactions. Another interesting example in Norway was a swimming pool. This was a swimming pool in a spa session in a hotel, and the temperature in the water and in the air was around 35 degrees, which is a very good conditions which will accelerate alkali aggregate reactions. So they realized just after a very short time something started to happen. They saw that tiles were falling off, and when they looked at the concrete, they saw the concrete also was cracked. So this happened quite fast because you had a high temperature, you had the reactive aggregates in the concrete and so on. So you see the crack width which was developed with the tiles, and if you went under the structure, under the pool, you can see in the basement the development, first after 1.5 years in service, then 2 years of service, and then 2.5 years in service. And eventually this swimming pool was demolished due to too much cracking and not possible to stop the expansion. There are also many examples around the world. Here some examples from Switzerland. On top you see some railway sleepers starting to crack, and also at the bottom a beam on top of a house which definitely have been expanding, as you can see indicated by the red arrow. This was a bridge in Canada. Now it's been demolished due to AAR, but that was heavily cracked, and probably with some interaction of some freeze-thaw deleterious as well. But you can see the whole structure here is very severe cracked. There are also problems with pavements, in this case pavements in US. Pavements both in airfields but also in roads. In airfields it's very critical because when the airfield is starting to crack up, there will be some loose parts, and that concrete pieces that could be sucked into engines of airplanes and so on. Of course, that is not a very good situation. And actually in Norway, it was a need, and one airport that started to get cracked like that. They need to remove the whole concrete pavement and replace it with a new pavement with a non-reactive composition of the concrete. Here is a concrete road in Canada. The concrete road was built with some every 20 meters or so, 20-30 meters. They had some expansion joints to enable some thermal expansion and so on. But as you can see, the concrete road it's been estimated an expansion of 0.2 to 0.3%. That means that the concrete they are expanding and the joints are just exploding in a way. So you can see that every joint has been pressed together and pressed too much together, so that the slabs have been pressed up. So this is the effect that could happen if you have a reactive composition in your concrete, and the expansion will continue like this. So let's go a little bit backward and think about, or start to look at the history of alkali aggregate reactions. It was a guy called Thomas Stanton back in 1940, working in the Californian State Division of Highways, that realized that some of the concretes in California started to crack. And in California they did not have any freeze-thaw attacks or so on, so it must be something else that happened. But he did a lot of studies on this, and he demonstrated many things that still are very valuable and that we are still looking into today. He realized that the alkali content, he used mortar bars, and he saw the expansion of the mortar bars, and he saw that the alkali content of the cement was critical. He also realized what I have mentioned, that we have different types and amount of reactive silica in the aggregates. And he also realized the importance of moisture, and that temperature will accelerate the reaction. And he found that if you had a cement, a low alkali cement, you could mitigate the reaction. And actually he also realized that expansion could be reduced by adding pozzolans like fly ash, silica fume, etc. So he did a great job. So the main question actually is, what have we learned since then? This is in 1940. Since then we have been developing test methods. Actually Stanton, he developed this mortar bar test, which was named the ASTM 227 test. Has been used for many years, but it has some limitations, so it's been redrawn during the last years. And then later on we get an accelerated mortar bar test developed in South Africa, which also has been an ASTM method. So we have been testing for decades, developing different test methods and so on, and different test methods in different countries. So it's been difficult to compare. And actually it's been held a lot of international conferences on this topic. It started back in Denmark, the first one in 1974. Then next year, 1975, it was held in Iceland. And then it was held every fourth year, big international conferences, and producing thousands of papers on this topic, on alkali aggregate reactions, how to test, how to mitigate, etc., etc. So we have a lot of proceedings, we have a lot of papers, we have a lot of information, but dealing with this. So we are still dealing with the test methods. How should we test? How should we determine reactive aggregates, reactive concrete compositions, etc. In a way to make this a global effort, we have been during a long time now, dealing with this on a international or on a global approach. During the RILEM Federation, or association. RILEM is an international union of laboratories and experts in construction materials, system and structures. And RILEM is a worldwide organization. So through RILEM, we have been able to develop test methods and approaches that could serve on a global scale. So actually the first technical committee in RILEM was established in 1988, and mainly focusing on accelerated aggregate testing, what kind of aggregates are reactive or not. And then the next TC took over in 2001 to 2006, looking more into diagnosis and appraisal and specification in existing structures and so on. And then continue into the third technical committee from 2006, which terminated in 2014, where also performance testing and modeling of structures were taken into account. And all those three technical committees were led by Dr. Philip Nixon from UK, and the secretary was Dr. Ian Sims, also from UK. So they did a tremendous effort in order to try to combat AAR. So the main outcome of this work has been that we have developed this RILEM test models, a three-step test procedure, starting by a petrographic examination. In this petrographic examination, which is called the AAR1 method, you're looking in microscope to see what kind of aggregates do you have, do you think it's reactive or not, and so on. Then the second step in the testing procedure is to do an accelerated motor bar test called the RILEM AAR2 method, where you are accelerated under high temperature and high alkali load to see if your aggregate is reactive in the mortar. And then finally you have the third step, which is a concrete prism test, where you also are taking into the coarse part of the aggregates and you're doing a concrete mix, and you are accelerated that under, it could be 38 degrees or it could be 60 degrees, to see how those concrete prisms are expanding. But what I've been lacking is kind of comparing those tests in the laboratory to what is happening in the field. So it's been a discussion or a challenge to try to relate those test methods in the laboratory with what's happening in real life. So that's why we have tried to develop those performance tests and compare with what is happening in field exposure sites. Just have a look first at the first step of the test methods, the petrographic method, which is called the RILEM AAR1 method. You are making thin sections of your aggregates, one thin sections in the 1 to 2 millimeter fraction and two thin sections in the 2 to 4 millimeter fractions of your aggregates, and you're point counting those thin sections under a microscope. And you are recognizing if those aggregates are reactive, maybe reactive, or innocuous. And then you're counting and you're getting a number. If you have a natural aggregate, that could be a combinations of different aggregates or rock types. If you have crushed rock, it could be just one rock type and so on. But you are measuring and assessing what kind of aggregates you have. In Norway, we have a critical content of 20%. If you have a natural aggregates and you get less than 20% reactive aggregates in your aggregates, then it's okay. However, if it's more than 20%, you have to regard your aggregate as reactive. So this is the first step in your assessment. And in Norway, we also have made a classification chart where you to the left have 4 groups of alkali reactive rock types. with some subgroups of rock types. Then in the middle you have your ambiguous rock types, and to the right, the green box, you have your innocuous rock types. So total 9 groups, and you're grouping your aggregates with this scheme. We also have been developed both in Norway and in Europe and global some atlas, some atlas where we have taken pictures of micrographs in the microscope, and you could see what kind of typical rocks are reactive and so on. So you could go to the website of harin.no. You will find a link to a Norwegian petrographic atlas, and also a link to a European atlas seen here to the left. The second step of the testing is the accelerator multiplier test. So in the accelerator multiplier test, you're actually taking the sand fraction of your aggregate. You are casting these multibars, and you are putting them in a high solution of sodium hydroxide at 80 degrees. So it is a very high solution of alkalized sodium hydroxide. It's a high temperature, and then you could get the expansion after only 14 days. And you are measuring the expansion between the edge studs of those prisms. As RILEM AAR2 method, this is a method only to measure the reactivity of the aggregates. However, on some places they are using this multiplier test to also test the performance of the different binder, the different cement and pozzolan and so on. But there are some questions about that due to the reason that there are some very high excess of alkalis used in this test. I looked in my PhD work back in '95. I looked at this accelerator multiplier test. And I found a very good correlation between when I looked into the grain sizes, or the crystal grain sizes of quartz or Norwegian aggregates, as you can see on the x-axis here, and related to the expansion after 14 days in the multiplier tests. So I counted the crystal size of quartz grains in different aggregates, and I calculated the total ground boundary area of quartz as square meters per centimeters in cubic, and you see the relation there. That work was also follow up by Nelia Castro. I was the supervisor for, and she back in 2012 also finished a PhD at the same university in NTNU in Norway, also looking into these issues, comparing microstructural features of quartz compared to the expansion in the multiplier test. Then you have the third test step, and then you are making real concrete. For instance, prisms 75 by 75 by 285, and you are real concrete with both the sand and the coarse aggregate used. And you have the RILEM AAR3 method, where you are storing those prisms in 38 degrees for 1 year, or you have an even more accelerated version, the RILEM AAR4, where you're storing them at 60 degrees, and you could measure the expansion after 20 weeks. And in the PhD by Dr. Lingard, he looked into different parameters that affecting these tests. First, we originally had some wrapped prism to try to reduce the alkalis leaching out of the prisms, but he realized that unwrapped prisms gave less leaching. He also looked at the temperature, 38 degrees versus 60 degrees and even 80 degrees. And he also saw that, for instance, the prism size, if you get a bigger prism size, up to 100 millimeters, you get less leaching. So he is recommending that the prism size should increase to get less leaching out of the prisms during the storage. And he also looked into the preconditionings, the curing of the samples, etc. Because the main question we are dealing with is that we have been developing these test methods in the laboratory. We are accelerating the prism by elevated temperature and so on. And then it's the question, and we do know that there will be some leaching in the laboratory. And then it's the main question, do we compare apple and pear? So what do we do with real concrete in real structures or in bigger samples stored outside? So we have been comparing results from what we see in the laboratory to what we see in the field, because that will give us the correct answer in the future. Because we do know that the effects of temperature and so on could be different on the outcome of what you get on the expansion. We see in typical concrete prism test at 38 degrees is flattened out something like this over time, and that is probably due to that the expansion is starting to leach out over time, and it's flattened out. Similar you see for 60 degrees. It's starting more rapid, but it's flattening out more rapidly as well. Probably that the leaching is starting earlier in the 60-degree test compared to the 38-degree test. And if you have a slow reactive aggregate in the 38-degree test, it will develop something like this. But if you have a slow reactive aggregate in the 60-degree test, it will follow very much the same pattern as the normal expansion. However, what we see if we are making bigger blocks and putting them outside, we'll see that the expansion is going something like that. So this is a field cube outside. It's starting, of course, slower, starting with some shrinkage, but then it's starting to expand, and it seems to expand and expand and expand. So it's obvious a different pattern in the field compared to what we see in the laboratory. So the question is that this disagreement, is it due to alkali leaching in the laboratory testing, that you have relatively small prisms, so you get some leaching out of it? Or is it a temperature effect in the laboratory compared to what we see in the field? We do know that the temperature has a big effect of what the outcome. If you have some accelerated conditions, just like as an example, take this egg and you're putting them in an accelerated conditions, 100 degrees. After 6 to 8 minutes, you will get some boiled eggs. If you take the same egg and put it on a more realistic exposure conditions at 38 degrees, you will get the chicken after 28 days. So the effect of the temperature is quite important to realize when we are comparing what we got in laboratory compared to what we got in. So it was started quite early to develop these outdoor exposure sites down to the black-white picture you see from UK. To the left you see the outdoor exposure site in the University of Texas in Austin, and you have also a very big site at CanMet in Ottawa in Canada. So those sites you're able, well, they are mixing all kinds of different concrete and types of aggregates, and they are measuring expansion and comparing also to what they are measuring in the laboratory. We also have been developing various sites in Europe. We had a site in Valencia in Spain, which of course is more humid and warmer than Northern Europe. We have one Düsseldorf in Germany, one in Reykjavik in Iceland, and we see the different in the different sites. And we are using those results to compare what is happening in laboratory compared to field. When it comes to the European standardization, is a little bit tricky because it is not we do have a lot of European test standards for aggregates and so on, but we don't have a European test standard for alkali aggregate reactivity, because it says in the 2002 version of the aggregate standard 12620 that when required, the alkali silica reactivity of aggregates shall be assessed in accordance with the provision valid in the place of use and the results declared. That means that more or less each country is dealing with this situation. How the future will be, it's difficult to tell, but this has been the situation in Europe, that each country needs to deal with this situation, both testing and mitigating effect regarding deleterious AAR. In Norway, we developed quite early recommendation by the Norwegian Concrete Association. It is in Norwegian, and it's translated. It said how to produce durable concrete with alkali reactive aggregates. That means that in Norway we are allowed to use alkali reactive aggregates if we are following this procedure in this publication number 21 from the Norwegian Concrete Association. In Norway we are following the same three-step procedure as in Rylem, starting with a petrographic analysis. So we have this general limit of 20% of reactive rock types. If it's below that 20%, everything is fine. However, if it is more than 20%, you should regard your aggregate as reactive and you need to take some precaution. Then you have the accelerated mortar bar method testing the aggregates. And that is some different critical limits for different combination of fine aggregates, coarse aggregates, and so on. And then eventually you have the third step in Norway with the Norwegian concrete prism method. It is slightly bigger concrete prisms. They are a diameter of 100 millimeters, and you're measuring the expansion at 38 degrees up to 1 year. And then you have some critical limits on that as well. But in Norway, we also have been introducing the performance testing concept. So we have taken the worst case aggregate we know about in Norway. It is cataclysite, which is reactive, relatively high reactive. And then we are making this test with different binders. So we have one binder with a high alkali level, one with a medium alkali level, and one with a low one. And we are testing back and forth, and we are finding where this expansion is reaching above the limit for accepted expansion. And then we could try with different cements and so on with this worst case aggregate. And we also taking away a safety factor, and then you will get for a certain binder or a certain cement with a pozzolan or a low alkali cement, etc. You could get a limit for accepted alkali content. And this has been tested for different cements and binders and so on. And we do have different tables in the Norwegian regulations. So for instance, if you have Norcem standard fly ash cement, you are allowed to use up to 7 kilos of alkalis per cubic meter of your concrete. How to calculate the alkalis in the concrete is described in detail in this publication, but you're taking the alkali percentage in your cement and multiplying with the kilos used in your concrete, and you'll get this number, kilos per cubic meter of concrete. So this was the Norwegian approach, and we are using that, and we are feeling quite confident that it's working very well in Norway. With the worst case aggregate, we are able to put some critical limits for the different cement used and so on. And in that sense, we are making durable concrete in Norway, even though we are using alkali reactive aggregates. But in the RILEM work, that was, I told earlier about the 3 different RILEM technical committees. They ended up with some publications. The first one in 2013 about a guide to diagnosis and appraisal of AAR damage to concrete in structures. And then in 2015, the RILEM recommendations. There you have all the detailed test method description of the AAR1, the petrographic method, the AAR2, the accelerator motor test, AAR3 concrete system test, etc. And in addition, in 2016, it was published a very detailed and thorough petrographic atlas with examples from all around the world of different reactive rock types. So very, very good, nice micrographs presented in that book. So that was the outcome of these 3 technical committees. But after the 3 technical committees, we realized still that we need to continue of the development of performance testing. And also to look into the exposure sites at different environmental locations, warm and hot, like in Texas, cold and wet, like in Reykjavik, etc., and comparing the results. And also we took into account that we do not know so much about the releasable alkalis, the potential contributions of alkalis from aggregates. So we started a new technical committee back in 2014, and that committee was led by me, and we finalized our findings end of last year. And now in April 2020, we are submitting new test methods about alkali release called AAR8, a new performance test method with the bigger concrete prisms called AAR10, and also versions with a higher temperature at 60 degrees called AAR11 and AAR12, and also an approach where we are wrapping the prisms with some alkali to compensate for the leaching called AAR13. So this is the work that has been done in the 4th technical committee of RILEM, and at the moment there are no technical committees working on this issue, but probably in the years to come we need to look more into the releasable alkalis and how to count for those alkalis coming into the system from the aggregates. So that was about alkali aggregate reactions. Now at the end of this presentation, I briefly will add a little bit about another deleterious mechanisms caused by aggregates, and that is the oxidation of pyrrhotite. It is a similar, in a way, reaction as AAR, even though it is different. So I just briefly will present some slides about this mechanism. What is happening is that if you have an aggregate with containing pyrrhotite and you are putting that pyrrhotite or this aggregate with pyrrhotite into your concrete. It could over time start to oxidate. So if you have oxygen and water, you will have a reaction, as you can see, and you will have some products out of that reaction. So you will have some iron, some rust products, which will, the rust itself will create some expansion in the concrete. But in addition, the reaction will also produce some sulfuric acid. And the sulfuric acid will also secondarily lead to some development of attendrite, gypsum and thaumasite formation in your concrete. And then you could even have some bigger expansion. So it is a different chemical mechanisms, completely different from AAR, but it is leading to expansion by aggregates in the concrete. Particularly in Canada, they have seen some bad cases related to pyrrhotite in the aggregate. You see some examples here in the foundation of a domestic house in Trois-Rivières in Canada. And if you look closer, you see that up to the left that the wall is started to crack. It could look similar as AAR. Closer to see that the cracks, they are much bigger, and this is happening much faster. So it is a very serious reaction. And what they needed to do in this region, there was no way of repairing that concrete. So they just lifted those buildings and removed the walls under and replaced with new concrete. So that was the solution in that area. Now this pyrrhotite challenge is a major research of major research interest in Canada. So they have just started quite a big project on this at the University of Laval in Quebec City, looking into how to test these types of aggregates, how to potentially mitigate it in concrete, and so on. Also in the States, they have realized some problems. A recent paper is describing the pyrrhotite epidemic in eastern Connecticut, about diagnosis and prevention. So they also have major problems there. So this is a topic that we are realizing in addition to alkali aggregate reactions, which we have been dealing with for many decades. But now we are also realizing that this kind of expensive aggregate mechanisms could be a big problem. In Norway, we haven't seen any major damage due to pyrrhotite in concrete aggregates. However, when they started to build a follow link project in Norway, which is a tunnel from Oslo southwards, they are drilling it with tunnel drilling machines. And the original plan was to use the local bedrock from the tunnel, crush it, use it both as the coarse and the fine as the major aggregates in the element production. You see the elements to the right. The elements are lining the concrete, the tunnel. So you have the concrete linings of the tunnel. But when they started to take samples of the bedrock from the tunnel, they realized that the sulfur content was above what is accepted, and it was also indication of pyrrhotite. So it was decided to stop using the bedrock, the local aggregates, and instead buy some external commercial aggregates. So it has had a big impact on that project, even though it hadn't made any damage. but it had an economical impact on that project. And as a consequence, we are into this topic in Norway. We had the pre-project, which we had the international workshop in 2018 in November in Oslo. We made the proceedings from that workshop. And last year we also made a state-of-the-art report in Norwegian about the pyrrhotite in concrete aggregates. And we are now heading for a main project, including at least one PhD and maybe one PhD in addition, or a postdoctor. So the pyrrhotite is now a new topic in Norway, and we need to look into it, how to quantify it, and also how to potentially find test methods and how to mitigate it in future concrete structures. So that was the presentation today about alkali aggregate reactions and a little bit of oxidation of pyrrhotite in the end. Please also visit the other presentations I have on my YouTube channel about aggregates for concrete and other issues. Bye bye.